Hi, and welcome to this clip on corrosion and rusting. I'd like to start things off by introducing you to my bike, or more importantly, the left crank of my bike. No, I haven't suddenly lost my mind. There's a reason for this. I've got a question for you. How come on the left-hand crank of my bike, where that is worn against the boots I cycle in to work, how come you can actually see the reflection of the iPad I took this picture with in the metal, but at the same time exposed to the same amount of rain and salt and grit and all sorts of stuff on the road? If you look at the bolt that holds the crank in place, how come it's rusted in the middle? The key to this is chemistry of metals. In this case, the crank arm is made of aluminium, but the bolt holding the crank arm in place is made of iron. One has corroded and rusted, the other one hasn't shown any corrosion at all. I guarantee you I've not touched up that crank arm. It is actually as shiny as it seems in the picture. So why? What's going on? Now, I live in Brighton on the south coast of England, and I cycle to work every single day. It doesn't matter whether it's raining or whether it's not. And living by the coast, it means we pick up probably more than our fair share of rain. And obviously the air is quite salty because it blows in off the sea. So it soon becomes quite apparent which bike parts tend to survive those kind of conditions and which bike parts need replacing regularly because they keep rusting. Like I suggested in the previous slide, it's down to what's made of iron versus what's made of aluminium. But hang on a minute. Don't you get taught in school that aluminium is more reactive than iron? Well, this is actually true. It is more reactive than iron, so how come it doesn't corrode in the same way? The key is in what it actually does. So, in an ironic twist, aluminium actually is more reactive towards oxygen in the air than iron is. But what happens when aluminium reacts with oxygen? It produces a very, very tough oxide layer. So this aluminium oxide layer that formed on all aluminium surfaces that are exposed to air, it has the following advantages. It forms immediately and it's very chemically stable, so it forms a protective barrier to further reaction. So when we apply this to load-bearing structures like aluminium bike frames, the metal that the frame is made of underneath is protected effectively by the reaction. And as such, it maintains its physical and chemical integrity. So let's apply the same idea to iron. If iron is less reactive than aluminium in the reactivity series, how come steel bikes corrode more easily when they're exposed to wet, salty conditions, such as that found on coastal rides or maybe on salted roads in winter? So the chemistry involved in the corrosion of iron is a little bit more complicated, because we don't just involve iron and oxygen, water actually plays a chemical role too. So in order for this bit to make sense, it's worth recalling that these reactions are all redox reactions, and as such they'll involve electrical potentials. So a half reaction with a more positive electrical potential will reverse one with a less positive electrical potential. So if we look at one possible half reaction that water can undergo, it's a slightly unusual one, but it can take place in certain conditions, and it does carry its own electrical potential of minus 0.42 volts. Now if we assume that this water, the source of it is either water on the road or perhaps rain, and we've got an object made of iron, and the iron is exposed to the water. So if we look at a typical reduction of Fe2 plus into Fe, and we imagine that our bike frame, for example, is made of iron. If you look at the two values, you can see that the top value, minus 0.42 volts, is marginally more positive. So that means the bottom one is reversed. So So if your frame is made of solid iron, it's going to tend to turn into Fe2+. So what happens is the reaction proceeds as shown at the bottom of the screen, and your precious iron bike frame, which starts out as solid iron, ends up as Fe2+, which is no good to anybody in terms of engineering strength or structural integrity. So in other words, the water is causing it to create Fe2+. The Fe2+ then forms rust. Now if you look at the difference in the electrode potentials, there's actually a very slight difference, so this will happen very, very, very slowly. The problem starts to arise when oxygen gets involved. Now, oxygen reacts with H+ ions in aqueous solution and becomes 2 moles of water, and it has an electrode potential of plus 1.23 volts. So what you've got to remember is that the iron has to actually become Fe3+ in iron 3 oxide, which is rust. In order to achieve this, this means that the iron in the form of Fe2+ has to actually be further oxidized. So therefore the reduction of oxygen in H+ to H2O has to take place in the presence of Fe2+, and the Fe2+ going to Fe3+ carries its own half equation. And that half equation is shown now, and the value for that half equation, the electrode potential, is less positive than the one for oxygen going to H2O. Therefore, because those are the two ingredients that are mixed with each other, the oxygen and the Fe2+, the bottom one is reversed. So by combining those two together, the Fe2+ can be oxidized further to Fe3+, and therefore be in a position to form iron 3 oxide. So it first undergoes a reaction with OH- to form FeOH2, and then in the presence of oxygen from the air, this undergoes further oxidation to become FeOH3. So what happens next is this FeOH3 is the beginnings of the formation of rust. So over an extended period of time, this eventually decomposes and forms hydrated Fe2O3, which is in the box. So there's actually several decompositions that can take place. The value for X can be variable. We'll look at one of the examples in the next slide anyway. But the actual rust that we see long term is Fe2O3.XH2O. So coming back to the idea of salt, that's one of the key ingredients. So in the electrochemical system for salt, electrochemical system for rusting, if there's salty water, what takes place here is that the salt acts as a salt bridge. So in other words, the droplet of water on the rusting surface actually carries the charges back towards the original, the anode. So I'll look at the actual, the detail of what happens at the point at which rusting takes place in the next slide. But remembering electrochemical cells from A level, you need not just an anode and a cathode where the two half equations can take place, but also a salt bridge that allows the completion of the circuit. But first let's look at what happens, some possible reasons why the FeOH3 actually does decompose. So it takes a little bit of thinking about the structure of FeOH3 and also some of the energetics that might also be involved. So let's have a look at simplifying a possible reason why iron hydroxide would decompose into iron oxide hydrated, which is rust. So first of all, the iron hydroxide would decompose into iron oxide and water, and if they're in the correct molar proportions, they'll form one of several different hydrated iron oxide crystalline structures. Remember, the X value for XH2O in the previous slide wasn't necessarily saying it's only one. It may be several values. This is one possibility. So let's explore just this possibility. So this structure has 6 coordinate bonds, which are a type of dative covalent bond. And any type of covalent bond involves the sharing of electrons. But if we look closely at what a covalent bond actually is, it's not just the sharing of electrons, it's the electrostatic attraction between those two electrons and two nuclei, one from each bonding atom. This is energetically a little bit less favourable than maybe one nucleus in one atom gaining an electron or gaining electrons, as happens in ionic bonding. In other words, it's more energetically favourable for the same number of iron, oxygen and hydrogen atoms to form a stable ionic lattice such as Fe2O3 than remain in a covalent arrangement such as found in the FeOH3 H2O3 solid complex. So if you look at the charge on the Fe3 plus and the charge on the O2 minus ions in your final rust product, it's a difference of 5. This will lead to a stronger attraction between the ions. As such, you'd get a lowering of energy, because any attraction between two species is an exothermic process. And if you lower the energy in the system, you increase its stability. So it's favourable for the decomposition to take place. The exact mechanism by which it happens, I actually am not sure about. So I'm not going to try and guess and put something down that's incorrect. But hopefully the idea of high charge difference leading to stronger attraction, therefore a lowering of the energy during that transition and an increase in stability, is fairly easy to understand and accept using A-level ideas. So if we use Hess's law to work out what the delta RH value is for that conversion, we can apply these values and work out what the indirect route would be. So in terms of energy, at least it's exothermic, so on the face of it, it's likely to happen. Obviously, we need to look at the entropy as well. So we now need to look at the entropy values for each of the transformations and see what we get. And then we can finally work out what the delta G value will be. And then that will finally tell us whether that decomposition is feasible or not. So using the standard entropy values for each of the reactants and products, that gives us minus 83.7 joules per Kelvin per mole. Now what we need to do is work out the feasibility of the process. And we use that using the Gibbs equation. So first we have to collect and convert any units. So our delta H is in kilojoules per mole, so we have to convert our delta S into minus 0.0837 kilojoules per mole to the minus 1 per Kelvin to the minus 1. So what we've got to do now is work out the minimum temperature at which this reaction becomes feasible. To do this, we have to assume that delta G is 0. So seeing as both delta H and delta S are negative, with that set of conditions, what happens is that the feasibility is possible at low temperatures, but not possible at high ones. So therefore, the maximum temperature at which rusting is feasible is 432.5 kelvins, or 159.5 degrees Celsius. So if we do the calculation, that gives us 432.5 Kelvin, or 159.5 degrees C. So this means that below 432.5 Kelvin, delta G remains negative, and rusting remains feasible. So, suppose you have all of these things in place you need to start the chemical process of rust. What actually dictates where the rust starts on the surface? So this is a cabinet that's now stored inside, obviously, but at one point it was stored outside. So you can see where rust started to form, but that doesn't necessarily represent places where the paint chipped off. perhaps when it was being moved around, the paint up here might have chipped and caused the rust to happen. But what about here? Could it have been scraped off maybe? Or what about here? So what we've got to think about is what might be causing this. So if we take a sheet of iron that's unpainted, we imagine that we have these areas on the surface of the iron that can't be seen with the naked eye, that contain impurities or imperfections in the metallic lattice. They're actually more likely to be tiny little spots here and there. The lower the quality of the iron, the more likely these are to form. The higher the quality of the iron, these will be processed out a bit. Whereas nearby, in another place where there is impurities, electron density might be lower than its surroundings. So if you get two of these spots that are close to each other, that are invisible to the naked eye, you can get an electrochemical cell eventually forming between them. If the iron is exposed, and we have oxygen from the air, it gets rained on, and the rain contains dissolved ions. We have all the ingredients we need for an electrochemical cell to be set up, complete with salt bridge. So therefore the chemical reactions we looked at in the previous slide can start to happen. So if we take a closer look at the structure of our metal lattice and take a cross-section of our iron, there are two areas very close to each other that are impure. One area has greater electron density and another area has lower electron density. Remember that in metal lattice you have delocalized electrons. So if you have impurities or imperfections in the metal lattice structure, some areas might have more electrons present in that delocalized cloud than other areas. So that means that one area can become relatively positively charged and the other area can become relatively negatively charged. So in order to balance this imbalance of charge between these two areas, the area of a greater electron density becomes negatively charged. Well, it is negatively charged, so what happens is the reaction that's going to tend to set up there is an oxidation. So it's the Fe2 plus Fe half cell, which, as we know from the previous slide, is actually reversed. So you get a flow of electrons through the metal. However, what that will do will slowly reduce the negative charge on the left-hand side and slowly reduce the positive charge on the right-hand side. Now, without an ability or a wherewithal for the charge to flow back from right to left, the reaction won't last very long. So this is where the water comes in, or specifically the rainwater with ions dissolved in it. So if we now have some rain or water that gets onto the surface at the point at which these two imperfections in the metal lattice exist, you now have the wherewithal for a salt bridge. So the water containing dissolved ions acts as a salt bridge. So if the water acts as a salt bridge because it contains dissolved ions, that means that ions can flow from right to left, from positive to negative, to balance the charge. So therefore we have an electrochemical cell that can set up, and eventually rust forms. So during the series of chemical processes we talked about in the previous slide, we eventually get our rust. And once the initial rust has formed, it itself acts as an impurity. So therefore that then counts as new areas of impurity in the iron surface, so the process can start again and again and again. So this is how rust tends to perpetuate and spread and work its way under paint. So it's actually a very, very difficult process to stop once it's actually begun, because it encourages its own continuation, if that makes sense. So the thing to remember is if you have areas of impurity on the surface of the iron, we have all the ingredients in place once rain has happened and oxygen has been exposed to it, and we have water in place for the rust to start. And once the rust actually begins, that then sets up new areas of impurity on that iron surface, so it spreads further. So one spot of rust can actually become a much larger area quite quickly. So the first part asks us to name two substances other than iron that are essential to the rusting of steel. And those would be oxygen and water. Then it goes on to say the initial attack on the surface of the steel is electrochemical. Corrosion cells are set up on the surface of the metal with oxidation occurring at negative regions and reduction at positive regions. So we talked about this a little bit earlier when we looked at areas where positive and negative charge might set up. So at the negative electrode, you get Fe solid, the actual iron in the steel, turning into Fe2 plus aqueous because it's happening in the presence of rainwater or water from the road or wherever the water came from to start the rust. So at the positive region, you'd get oxygen and the water reacting, gaining 4 electrons and forming 4 OH minus. Obviously in aqueous solution. So the first stage of the rusting that we've looked at before is the combination of these. So moving the page down a bit, so we can have a look at the next part of the question sheet. It says, suggest why it is that rusting occurs much more rapidly in salt water than it does in rainwater. So thinking back to your work on electrolytes and on electrochemical cells, so the name of the solid compound formed in the products of the reaction in part 4 above is iron 2 hydroxide. As you can see at the top. So the next stage of the corrosion process involves the conversion of that compound into an iron 3 compound. So the ionic half equations show this, and as we said before, that happens in the presence of oxygen. It's the conversion of Fe2 plus into Fe3 plus. So what type of chemical reaction is represented? So it's obviously an increase in oxidation state, so we can call it an oxidation. And the substance would be actual oxygen from the air. Looking at the final part, it says rusting is off, or hematite is actually Fe2O3. As we suggested, the iron hydroxide that forms in the penultimate stage of rusting, and those would be oxygen and water. Then it goes on to say the initial attack on the surface of the steel is electrochemical. Corrosion cells are set up on the surface of the metal with oxidation occurring at negative regions and reduction at positive regions. So, I haven't gone into in this clip why these corrosion cells become established, because that's slightly outside its remit, but let's have a think about this.